Okay, section 6.2, circles, polygons, perimeter, and area. I'm going to spend more time here because there's more to say, more concrete calculations that we can do instead of last section, which was a lot of definitions, right? So, well, there are still going to be a lot of definitions in this section because we got to make sure we know the names of these shapes. First of all, a circle is not a polygon. Okay, so that's the first thing to take away from this table on page 263. A circle is the set of all points. All these shapes are in a plane, okay? A circle is a set of all points in a plane that are a certain distance from a fixed center point. So if you get some point, some center of the circle, pick some distance, which of course we call the radius, so we denote lowercase r, the radius of the circle. All the points that are equidistant from that center, I'm going to do my best here. But got pretty lopsided. All the points equidistant from this center point in every direction, that's called a circle. And the distance from the center to the outside is the radius, and the distance all the way across is the diameter. So of course we have that relationship that diameter is equal to twice the radius. Okay. Polygons, that's going to be pretty much every other shape you've ever heard of in your life. Straight side shapes, right, are shapes that are built from straight line segments, and they'll have to be closed, meaning you can't have something that's like left open, right? And then we have tons of different types of polygons that we can talk about that we have classified as triangles, quadrilaterals, and then within quadrilaterals there's rectangles, rhombuses, squares, parallelograms, trapezoids, all that good stuff. Then we have pentagons going up in the number of sides, pentagons, hexagons, etc. Octagons, like a stop sign, 8 sides. And then if you zoom out of polygons and just categorize them into 2 big subsets, you can have convex polygons, which is where all the sides are pointing out, they're convex, versus concave polygons where one of the sides or 2 of the sides are pointing in. So there's nice little pictures of that on this table on page 263. Some concave polygons versus convex. So you're probably more familiar with convex polygons. So all the interior angles here are measuring less than 180, whereas in a convex or a concave polygon, one of the angles, the one where it dips in, where it's concave, that angle is going to be greater than 180 inside. Okay. Okay, we have this nice rule for the sum of the interior angles of a polygon, of an n-sided polygon. N-sided meaning n being any number of sides. So we have this rule that if you take the number of sides and you subtract 2 and then you multiply by 180 degrees, this gives the sum of the interior angle measures of an n-sided polygon. So what would be for an octagon, and let's say for a stop sign, which is a very nice octagon because it has 8 sides, right? An octagon has 8 sides. But it also is a very clean octagon in that all the side lengths are the same and all the angle measures are the same, which I'm doing my best to draw here. So if this was a stop sign, what could we say the angle measures are? Well, since we know all the angles are the same, all the angle measures are the same, we can say, well, it must be the sum, the total, the total angle measure must be n minus 2 times 180. So we would say 8, because that's the number of sides, minus 2 times 180. So essentially getting 6 times 180, which is going to be 1080. You can just pop that into the calculator. 1080 degrees. Whoops, 1080 degrees. And if I wanted to know what is the angle, I want to know what each of these angle measures are. And I know they're all the same, and how many of them are there? Well, there should be 8, right? 1, 2, 3, 4, 5, 6, 7, 8, of course. So I would divide 1080 degrees divided into 8, which is going to give me 135. 135 degrees. So if you went up to a stop sign with a protractor and measured that angle, it would be 135 degrees. And it doesn't matter how big the stop sign is. In my little picture, if I had drawn it really well and all these sides are the same, then my angle measures here would be 135 degrees. And then if you went and got a real life stop sign, which is like as big as my desk here, and measured it, those angles would still be 135 degrees. Angles don't care how big the shape is. Angles don't care how big a shape is. Okay, and that's going to lead us straight into the next thing, which is similar shapes, in particular similar triangles. So they give us a definition here at the top of page 265, which says, two triangles are similar if the corresponding angles are the same, or congruent, meaning their measures are the same, and the ratio of the lengths of the corresponding sides are equal, meaning the sides are proportional. That's, remember the proportion section we talked about. We probably did some triangle, I hope, maybe we did some triangle examples there. If not, we're going to do some here. So I'm going to change the definition here, similar polygons, because this idea of similar shapes works not just for triangles, but for any polygon. So two polygons are similar if their corresponding, I'm going to say it's slightly different, angle measures. So I'm saying angle measures are equal. So they just said angles are congruent, but that's the same as saying angle measures are equal. Okay. Oh, and this is the useful part most of the time, and their sides are proportional. Corresponding sides are proportional, which means we can set up a proportion to solve for missing sides. Okay, so example 1 says we have this situation where we have a man who is 6 feet tall standing 20 feet from the base of a tree. Okay, so let's get this measured out. We have the tree here, we have the man here. This is 6 feet. The sun shines on the tree and the man and casts a 30-foot shadow. Okay, so we have this being 30 feet. Feet. And he's standing 20 feet from the base of the tree. Okay, let's see. There we go. And what do we not want to know? We want to know the height of the tree. Okay, first of all, the two triangles here are this little triangle right here. They're both right triangles, right? But that's actually not going to come into play. This is a triangle and then the bigger triangle. Okay. Oh, I didn't even write example 1. since these two triangles are sharing angle measures, right, obviously they're sharing this angle measure. They're also both right triangles, so these two angles are the same. And if those two angles correspond to the other two angles, then this one must also be the same, right? Because there's nothing else it could be because of the way angles in a triangle behave. In other words, they add to 180, meaning this last angle in both of these triangles must be exactly the same. Okay, so we have this larger triangle, which has side measure 30 feet here and unknown feet here, and then we have this smaller triangle which has measure 6 feet here, 6 feet, and this side here, which of course is 10 feet. Okay. So what we can do, since these triangles are similar, their sides are proportional, we can set up a proportion. X over 30 is equal to 6 over 10. Corresponding sides are matching across the proportion. X corresponds to 6, so they're matching across. 30 corresponds to 10. Okay, and remember the way we solve a proportion. You may already know what this one is because you can tell how the 10 has been scaled up, so you know that the 6 must be scaled up by a 3 as well. So you know it's going to be 18, but what if you didn't know, right? Or what if it was scaled up by some weird number that was unrecognizable? You would cross multiply, okay, 10 times x, 30 times 6, and then you would divide. Okay. Cool. Alright, coming up next is perimeter and area. Now for perimeter, you don't need formulas for polygons. You just need to know perimeter is the sum of exterior side measures Now this is only for polygons, right? For curved shapes, you have to have actual formulas. So for circles, you've got to have a formula for the circumference of a circle. But for straight line shapes, you don't need they give you all sorts of different formulas here. Well, actually, they only give you a couple different ones, but really it's just always going to be the sum of the exterior sides. And I'm making a point to say exterior sides because you may have a picture where you have two shapes squished together together to form a new shape. You would not add the internal line where those two shapes meet. Now we have area, and there are different formulas for area. Basically, for quadrilaterals, so for rectangles, squares, parallelograms, trapezoids, the area is basically going to boil down to length times width. So for rectangles, we have length by width. Those are the two measures, the two side measures. Area is going to be length times width. We have squares, which if we called it length and width again, it would be the same formula, but traditionally we say S for the side measure of a square. It doesn't matter. It's going to be the same, S times S, which is S squared. But again, it's the same formula, right? Just different notation, just different letters. Okay? And then a parallelogram, which has these slanted sides, we call the bottom length base, which is pretty much the same as width, right? And we call this measure on the parallelogram its height, and the area is base times height, so it's pretty much the same again as a rectangle, right? Just different letters. And in fact, if you look at this and consider this little tiny triangle I've drawn here, if I erased it, flipped it over, and put it over here, I would have a rectangle with side measures B and H. And then finally for the trapezoids, what we do is we have the height again, just like a parallelogram, and then we notate the two bases as base 1, so this is this top base, and base 2, And the way you find the area for a trapezoid, so that's B sub 1 and B sub 2, in case you can't see it. I'll draw it bigger over here. That's H. B1 and B2 is you find the average of these two side lengths of the two bases. So this formula is going to look worse, but it's really just the same thing again. You're going to find the average of those two bases, B1 plus B2 divided by 2. That's how you find an average of two numbers. And then you multiply by the height. So pretty much all of these are like base times height, base times height, base times height, and then some new base times height. That's quadrilaterals. Then we have triangles. The area of a triangle is going to be one half base times height. So its height not coming from the slanted lines, its height is this vertical distance from its base to its highest point, and of course its base is just whatever is laying parallel to the floor, right, to the bottom, whatever it's resting on. So it's pretty much again like the same, we have base times height again. Same as a quadrilateral, except for the 1/2. That 1/2 is always going to be there for triangles. And if you think about it, it makes sense. If you take any triangle, copy it, flip it, and stick it to the other triangle, you're going to have a parallelogram. And an area of a parallelogram is base times height. Okay. So with all that being said, let's run some examples here. Let's do example 4. We'll skip example 3. Example 3 is just about counting grid spaces, which, well, it's not completely about that, but in example 3, A and B, you can literally just count up the grid squares to find its area, which is kind of the point of area, right? It's like counting up grid squares inside. For C, it's a bit more complicated, but you can just count up the grid squares of its height, which would be 5, and its base, which would be, I think, 7 or 8. Yeah, 8, and then just find the area that way. Okay, so I want to go to example 4, which is a bit more interesting. We have some kind of... So this is supposed to be straight there. Some kind of weird, maybe a floor plan or something. Or maybe this is like a wall that you're trying to paint and there's like a door here and you're just trying to get a real quick rough estimate for how much paint you're going to need or something like that. Or this is some piece of wood that you need to buy. Or you're having work done on your house and you're having someone else do the work and they told you this piece of wood cost $120, so now you're doing the math because you think you're getting scammed or something like that. Who knows? Okay. Part A says to determine the area to be painted. Okay, so in the book, this is something that we're painting. So whenever you're painting something, you need to know its square footage so you know how much paint to get. So we want to find the area of this shape. Okay. Well, we can do all sorts of things with these side measures. First of all, I know the side measure right here. I know what it is. It's going to be the sum of this length plus this length, but this length here is 9, right? It's like that line segment problem we did in 6.1. It's just, if it's a finite length and you have the two pieces that make it up, take the sum of them to find the new length, 16 feet. Okay. 7 plus 9. Here, same idea. I know all the way across is 40. This piece here is 28. So how long should this piece be? Should be 12 feet. Or feet? Yes, feet, yes. Okay, so now I have every line here measured. But the question is, how do I find its area? I can either split it into two rectangles like this and have one really big rectangle and one small one, or I could split it here and have two like medium-sized rectangles. I could also split it like on the diagonal and make my problem really hard for me to make two trapezoids, but how about I do this? Okay, so I'll call this A1 and A2. What I'm going to do is find A1, find A2, take their sum. A1 is going to be 16 by 12, 16 feet by 12. And 16 times 12 is 152, is that right? Just pop it into the calculator. No, 92, sorry. 192. And I can say feet squared or square feet. I'll say feet squared like that. A2 is going to be 28 by 9. So not 40, right? 40 is all the way across over here. I want to make sure I'm using this side measure and this side measure. 28 by 9. And that's going to be 280 minus 28, 252, but I'll just pop it into the calculator. Yep, 252. Oh, let me actually write what I did here. 28 times 9, right? That's 252 feet squared. Take the sum of these two, A1 plus A2, to get 444 feet squared. So that came from A1 plus A2. Cool. Part B says, see, this is where we get into a little bit more real life. If a gallon of paint, so you're at Home Depot or Lowe's and you're looking at a gallon of paint and it says it covers 350 square feet. How many gallons of paint are needed? Okay, so clearly you need more than a gallon, right? You need more than a gallon, but they come in different sizes, right? You can get like a gallon and another gallon and have like a lot left over, or you can have a gallon and one of those little like smaller, like half gallon or pint or whatever. I don't know all the different sizes they come in. I know they come in very small, like a sample size or whatever, but for sure you can get like a half gallon. So maybe you're trying to figure out exactly how many gallons you need so that you know the cheapest route. Like you don't want to have any leftover paint. So we definitely know we need 1 gallon. And how many square feet are left over after that 1 gallon is used up? So we need 94 feet squared to be covered, right? To be covered. Okay. And that's, of course, just coming from the 444 minus 350. So we bought 1 gallon, which is going to cover 350 feet squared, or square feet, and we need this much more paint. So how do we figure out exactly how many gallons this would be? Well, if 1 gallon is 350, then what we need to do is we need to divide 94 by 350. And that's going to give us some small decimal amount, right? If it was 350 over 350, that would be 1 gallon, right? This is going to give us the small piece of a gallon that we need. So if we pop that into the calculator, so this is like literally the fraction of the square footage, 94 square feet out of 350 square feet. That's going to tell us the fraction of the gallon that we need. And it's about a little over a quarter, 0.27. This is now measured in gallons. So altogether, we need 1 gallon and a little bit more than a quarter gallon. So depending on how the store works, we could definitely get away with 1 gallon and then a half gallon. We could not do 1 gallon in a quart because it would be just barely not enough, right? It would be just barely not enough. So it would just depend on the store. You know, probably not going to be anything in between half gallon or quarter gallon and half gallon. So you'd probably have to go for a half gallon at the least. If not, just having to buy a whole nother gallon. Okay, example 5. We're finding the area of a parallelogram, which I've already talked about, so this will be very quick. In fact, so quick that I'm going to add something else to this problem. I'm going to say that angle measured there is 35 degrees. That's 35 degrees. Find measure of angle x. Okay, and then also find the area. And I'm going to add one more thing. I'm going to say this is 7 meters. Okay. Now the area of a parallelogram, I mentioned earlier, is base times height. So what side measure is not going to come into play in this calculation? The 7, right? Because the 7 is not base or height, it's the slanted line. The 7 would be very useful for finding perimeter. Right? If we wanted to find the perimeter of this shape, we would do 13 plus 7 plus 13 plus 7. But we want the area, so we're going to do 13 times 6, which is going to give us 78 meters, so meters squared. Okay, easy enough. Now what about the angle measure? Well, in a parallelogram, all the angles should be really nicely behaved. This angle is the same as this angle up here, so I know this is 35 and this is 35. And also the two obtuse angles are going to be the same. But what are they? Well, these two angles should be supplementary to each other, meaning the 35 plus the x degrees here should sum to 180. So that means we can set up a little equation, to solve for x. So x degrees is subtracting 35 from both sides. There we go. Easy enough, right? So the angle measures in a parallelogram are pretty much exactly what you would expect them to be. They look the same. These two small angles look the same, and they are. The two big angles look the same, and they are. And the small angle and the big angle look like they sum to 180, and they do. So all very intuitive there. Example 6 is asking us to find the area of a triangle. Find the area of a triangle. Okay, and they give us this. So it says a triangular plot of land has dimensions shown in the figure. A farmer wishes to fertilize the plot for spring planting. 1 bag of fertilizer will cover 15 square meters. How many bags of fertilizer are needed? Okay, so 1 bag is 15 meters squared. Alright, so we want to find the area and figure out how many bags he's going to need. So it's kind of similar to the gallons of paint thing, where we're going to find the area, then we're going to divide by 15. That'll tell us how many bags we need. Okay. So 12 times 31, first of all, to find the area. 12 times 31, that's going to be, 372 square meters. Okay, that's the total area. We'll divide by 15 to figure out how many bags we need. So 372 divided by 15. So if it was like 30, you would have 2 bags. If it was 45, that would be 3 bags. If it was 150, that would be 10 bags. What if it's 372? Well, just divide by 15. We're getting 24.8. So we'll say 25 bags, because you can't buy 0.8 of a bag. We're assuming that is not possible. Now at this point, the farmer may wish to say, maybe I shouldn't go to Lowe's and get 25 bags of fertilizer. Maybe I should try to go somewhere where they sell this kind of stuff in bulk, or maybe Lowe's does, I don't know. Like somewhere where you can buy it en masse, right? Like by volume, not by bag. Okay. Oh my goodness, I messed this problem up, didn't I? Look at me, oh God, and I can't even edit it out. Oh no, you're all gonna know. Okay. area of a triangle is 1/2 base times height, not just base times height. Okay, so it's going to be 1/2 of 372, which is 150 to 36. So 200 and let's just do it in the calculator because that's how we will all be doing it. 186 meters squared. Okay, so I accidentally found the area of a parallelogram with side measure, or with base and height 31 and 12. Okay, my mistake. So there it is, and then we divide that by 15. So same calculations, just got to take half of that. I forgot that 1/2 in the calculation. And that's going to give us, exactly half, so 12.4. He'll still need to buy 13 bags, right? 13, because he can't buy that 0.4. So, you may say, why are you rounding up? That's a 4, shouldn't you round down? But in the real world where you can't buy, decimal amounts, you in this kind of situation, you just got to step back and say, yeah, I need to round up to 13 because I still need this bit to be covered, and they don't sell fractional bags. Okay. Example 7 now is the area of a trapezoid. Find the area of the trapezoid. So we've got this side, this side. By the way, what is a trapezoid? It's just a quadrilateral where only one pair of sides is parallel. So you see, like a parallelogram has 2 pairs of parallel sides, like a rectangle. A rectangle is a special kind of parallelogram. But a trapezoid only has 1 pair of parallel sides, and the other sides are not parallel. Like, they may be both pointing in, or this and this. So trapezoids are a more general type of quadrilateral. Alright, how do we find its area? Remember, the area formula is going to be the sum of the bases divided by 2, so that's the average of those 2 bases, and then times the height. So plugging these numbers in, I'm going to have 12 plus 17 divided by 2 times 9. Cool. 12 plus 17 divided by 2, that's going to be 14.5. So that's the average of 12 and 17. We'll multiply by 9. 130.5. And what's the measure? Feet, so I'll say feet squared. Okay, easy enough. Just got to make sure we're using the right numbers. Now we're moving into circles. So with a circle, again, we have its radius here, its diameter. I already talked about the relationship between radius and diameter. The distance around the outside of the circle, so if you took the circle and cut it and laid it out flat, that distance is called the circumference, denoted by capital C, circumference, and that's going to be 2 pi r, or just pi times the diameter, because 2r is the diameter, right? So 2 different formulas there for circumference, and the area of a circle is going to be pi times the radius squared. So not making any substitutions with diameter in this formula, because 2r is not the same as r squared, right? Now, real quick note, pi is that special number. It's an irrational number. It's going to show up anytime you're dealing with curves. Anytime you're finding area, circumference, length of an arc, or something like that, anytime you're dealing with curves, you're going to see pi. So pi is approximately 3.14, but of course it's an irrational number, meaning the decimal part is infinite. So that means that whenever we're finding area and circumference, there's two ways to write it down. There's the exact form. Let me give you an example here. Let's just do a real quick one. We'll just say this radius is 3. It's 3. Then the circumference, the exact circumference of this would be 6 pi. Okay, so if you want an exact answer, you leave this little pi symbol, because this little pi symbol contains infinitely many digits. It holds all of its value in that little symbol. And its area, by the way, would be 9 pi, right? Pi times the radius squared. 3 squared is 9. Now, these are the exact forms. If you wanted an approximate answer, like a decimal number, you would use 3.14 for pi, and you would say 6 times 3.14 is 18.84. So these are just approximate answers, and 9 times 3.14 to get 28.26. Okay. So exact form, approximate form. Sometimes this is called leaving your answer in terms of pi. Okay, in terms of pi. Okay, let's do an example. Okay, example 8 says a fish tank has a circular top with a radius of 15 centimeters. Okay, circular top with radius of 15 centimeters. Jeff wants to cut a cover for the fish tank out of glass. Find the area and circumference of the cover of the tank. Okay. And we're going to use 3.14 as an approximation for pi, meaning we want the approximate circumference and area. Circumference is going to be 2 times pi times the radius. That's going to give me 30 pi. 2 times 15. And then that's going to be approximately, so I'll bust out the calculator and say 30 times 3.14, which is 94.2, and then centimeters. My area is going to be pi times the radius squared, so that's going to be 225 times pi. 15 squared is 225, and then to get an approximate answer, I'll plug in 3.14 for pi, multiplied to get 706.5 centimeters squared. So notice circumference is measured in centimeters, right? Single dimension unit, and area, of course, is measured in square units. So this is pretty big. 15 centimeters, that's... How big is 15 centimeters? Yeah, so it's and that's just its radius too, so it's a pretty big circle. Okay, example 9 says to consider the size of the lawn at a local park. The park consists of a grassy rectangular area determined by the dimensions 228 by 380 feet. Okay, 228 feet by 380 feet, so it's rectangular. Oof. Okay. This is 380 feet. This is 228 feet. We need to install circular sprinkles in the park in order to cover the grassy areas for the most complete coverage of the park grounds. The sprinkler has a maximum radius of 38 feet, and sprinklers will be placed in a grid-like pattern as seen in the figure. So a bunch of sprinklers like this. Bunch of sprinklers all over. We have 15 of them, so that's an important note. Without knowing, what the how many we have, this problem is a little bit different, right? It gets a little bit more complicated. But we know we have 15 sprinklers, so if they're placed in this fashion, how much of the grass will not get water. And we know the sprinkler has a maximum radius of 38 feet. And I think we're supposed to assume they're not going to overlap. They're not going to overlap. So what we want to do is we want to find the area of the rectangle. Okay, so that's quick and easy, 228 times 380. So let's just note that that is 86,640 feet squared. We're going to find the area of one sprinkler covered by one sprinkler. Its radius, remember, is 38 feet, so that's going to be pi times 38 squared. So 38 squared and then times 3.14. We're going to get an approximation here. So 38 times 38 and then times 3.14 is approximately 4,534.16 feet squared. And we know there are 10 of them. So the area covered by total sprinklers, let's say TS for total sprinklers, is that times 10. Because no, sorry, not times 10, God, times 15, sorry, times 15, right? Because there are 15 sprinklers. So 4,534.16 times 15 is 68,012.4 feet squared. Okay, now we're going to do the total area of the rectangle minus the total area covered by all the sprinklers, so total sprinklers. So that minus that, 86,640. We're getting 18,627.6, wait, 627, right? Yep. 0.6 feet squared. Cool. This is making a lot of assumptions, right? This is making the assumption that they will be placed evenly. There's no trees that are going to get in the way of this setup here, this grid-like pattern. We're assuming that all the sprinklers are pretty much exactly the same, assuming that there's going to be no overlap. Again, like the layout of the land would really matter here. Like, what if there was a tree, like right where we wanted to place this sprinkler, like a giant tree? Then it would have to scoot over a bit. Then there would be overlap with the one next to it. So that one would need to scoot over a bit because there'd be a big gap here, and all sorts of real-life complications that make problems like this much harder. But even with those kind of variables, this would be, in the real world, a good start, right? Just kind of a good start to say, okay, this is how much area, in the best circumstance, with no overlap, with each of these sprinklers maximizing the amount of area they can hit with no overlap, there's still going to be this much area left uncovered. And look, only one of them covers 4,500 feet. This is 18,000 feet. So we could use more. Even in the best situation, we could say, how many of those fit in here? Like four or five, right, well, closer to 4, right? That's a whole, 4 more sprinklers worth of area, right? Okay, so that's a nice real-world problem, or at least a model of a real-world problem. All right, that's it for this section.